Now let's take a look at a couple examples of evaluating these indefinite integrals. Now with that in mind, first thing that I'd like to try out is the indefinite integral of the quantity u plus 4 times 2u plus 1 du. Now keeping in mind that indefinite integrals are simply referring to antiderivatives, as long as you have all of your basic forms for antiderivatives down, these should be a piece of cake. Now, I will say this, a little bit of algebra can save you a lot of calculus. Trigonometric identities will help as well. So what we're going to do is FOIL this set and combine like terms. So first we'll have u times 2u, that'll be 2u squared. Outer will be plus u, and inner will be plus 8u for a total of 9u. And for last we'll have 4 times 1, that'll be 4. Now, taking an antiderivative, treating u as our independent variable, we'll be using the power rule a couple times in here. So power of u goes up by 1, divide by the new power. Power of u goes up by 1, divide by the new power. And for 4, that'll simply be 4u. Now, once the indefinite integral is done, this is the part where you have to put down your plus c to make sure that it is as general as possible. After that, the only manipulations that we're going to do to it will simply be aesthetic. It won't change really anything. It'll just put it into a slightly nicer form. So this function would be the most general antiderivative of the function u plus 4 times 2u plus 1. For another example involving the power rule, we'll take a look at the indefinite integral of 1 plus the square root of x plus x all over x. Now, once again, a little bit of algebra is going to save us a lot of grief. So first thing I'm going to do is distribute the x from the denominator to all 3 of the terms that are contained in the numerator. Then I'm going to reduce wherever possible. The 1 over x I'm actually just going to leave as 1 over x because that one has a special antiderivative. X to the 1/2 power divided by x to the 1 power would be x to the negative 1/2 power, and x divided by x would be x to the 0 power, better known as 1. Once in this form, all 3 of these terms are ready for their antiderivatives. 1 over x, as discussed with the antiderivatives section, will be the natural log of the absolute value of x. The other 2 can be evaluated using the power rule. So power goes up by 1. Adding 1 to negative 1/2 will give us positive 1/2 and divide by the new power. Dividing by 1/2 is the same as saying let's multiply by 2. Antiderivative of 1 will simply be our independent variable, which in this case will be x, and then we'll tag on the plus c at the end. So this serves as the most general antiderivative of this function, 1 plus the square root of x plus x all over x. Now, for examples that don't simply use the power rule, let's take a look at some trigonometric examples. So first one we have is the secant of t times the quantity secant t plus tangent t dt. So first thing I'm going to do here is try to get rid of my parentheses by distributing the secant. That'll give me the secant squared of t plus the secant of t times the tangent of t. We'll be finding the antiderivative of this. Both of these are basic forms. The derivative of what function would be the secant squared of t? That would be the tangent of t. And the derivative of the secant of t times the tangent of t would be the secant of t. Once you've completed your antiderivative, we stop writing the integral sign, and we do tag on the plus c. The differential goes away as soon as the integral sign goes away. Next up, indefinite integral of the sine of 2x divided by the sine of x dx. We have no quotient rule for antiderivatives, but we do have some identities that we can use. The identity that I'd like to use is the double angle identity for the sine. The double angle identity for the sine is that the sine of 2x will be equal to 2 times the sine of x times the cosine of x. So without performing the antiderivative, which is why I'm still writing the integral sign, we can transform the numerator into 2 times the sine of x times the cosine of x, all over the sine of x dx. At which point, we can use algebra to reduce the sine of x's, and we'll now be left with the indefinite integral of 2 times the cosine of x dx. Now, we're thinking of the function whose derivative is equal to the cosine of x, and we're just putting a coefficient of 2 in front of it. That would be 2 times the sine of x plus a constant. This represents the most general antiderivative of the function that we had listed above. Now, with that in mind, we shall try another example. This one is going to involve exponentials. So we have 2 to the t times the quantity 1 plus 5 to the t power. I'm going to begin by distributing that 2 to the t power to both of these terms. 2 to the t times 1 will simply be 2 to the t. And when you have the same exponent, you can multiply the two bases together. So 2 to the t times 5 to the t would be 10 to the t power. Now, the rule for antiderivatives for exponentials, like we have here, is it'll be the same exponential, but divided by the natural log of its base. So for 2 to the t, that'll be 2 to the t divided by the natural log of 2. For 10 to the t, that'll be 10 to the t divided by the natural log of 10. Once you make it to this point, tag on a plus c, and you are set.